So what I'm going to say rests on a certain bedrock, on a foundation, and it is this. The United States' ability to project power depends on information technology, and as such, cyber insecurity is the paramount national security risk. I'm going to repeat that. The United States' ability to project power depends on information technology, and as such, cyber insecurity is the paramount national security risk. Those of you with either an engineering or a management background know full well that you can't optimize everything at once, that requirements are always balanced by constraints. I'd like to suggest that in nothing of which I am aware is this so true as it is in cybersecurity, and the question of a policy response to cyber insecurity at the national level. In engineering, this is sometimes said as fast, cheap, reliable, choose two. In the public policy arena, we must first remember the definition of a free country, a place where that which is not forbidden is permitted. As we consider the pursuit of cybersecurity, we will have recourse to those two ideas time and again. I believe that we chance, at least, being faced with freedom, security, convenience, choose two. Some time ago, in a setting much like this, when I was asked to categorically state what sorts of risks were of a level that legitimately could be called a national security concern, my answer then was that only two kinds of attacks were that important. And like the Treasury Department's view on bank failure, that a public loss of confidence is to be avoided at all bearable cost, but that everything else amounts to some sort of private tragedy. The first of these two is any mechanism that, to operate correctly, must be a single point of function and therefore a single point of failure. The red telephone on the president's desk is just such a mechanism. 23 red telephones would be far worse than one. As such, that single red telephone deserves defense in depth, and defense in depth is simply a referendum on your willingness to spend money. Your willingness to spend money on layers. It is rarely, if ever, a research-grade problem. The other national security scale risk is cascade failure. And cascade failure is so very much easier to detonate in a monoculture, so very much easier when the attacker has to only write one bit of malware, not 10 million. The idea is obvious, believing in it is easy, acting on its implications is evidently rather hard. Despite what you may think by knowing a little history or something else, I am entirely sympathetic to the actual reason we continue to deploy computing monocultures. Making everything almost entirely alike is and remains our only hope for being able to manage it in a consistent manner. Put differently, when you deploy a computing monoculture, you are making a fundamental risk management decision that the downside risk of a black swan event is more tolerable than the downside risk of perpetual inconsistency. This is a hard question. And risk management, again, is about changing the future. Which would you rather have? The unlikely event of a severe impact or the day-to-day burden of perpetual inconsistency? Since that question, however, was asked, I've decided that there's now another national security scale issue, one that is a side effect of global supply chains and device complexity. It is simply no longer possible to provide product or supply chain assurance without a surveillance state, and perhaps not even then. I feel this matters philosophically and not just practically. The root source of risk is dependence. Dependence on system state, including dependence on expectations of system state. Indeed, my definition of security itself has co-evolved with my understanding of risk and risk's source, to where today I define security as the absence of unmitigatable surprise. I'll repeat that, the absence of unmitigatable surprise. It is thus obvious that increasing dependence means ever more difficulty in crafting mitigations, and that increasing complexity embeds dependencies in ways such that while surprises will grow less frequent, they will be all the more unexpected when they do come, and come they will. Many of you are familiar with Metcalfe's law, the idea that the value of a network is proportional to the square of the number of participants, or putting it differently, that the interactions are pairwise. If in the software world you were to admit that the interactions are not necessarily pairwise, what you get is known as Reed's law, which scales not as n to the 2, but 2 to the n. That's where the complexity is, and that's where our dependence has to be evaluated. And that is, frankly, the crux of the matter. Our dependence on cybersecurity as a society is inestimably irreversible and irreversibly inestimable.